So we've got, on this worksheet, we've got 3 problems to help us practice calculating delta G and K for different reactions. And the one thing that I want you to pay attention to is this phrase, as it is written. We're being asked to calculate delta G and K for the reaction as it is written, which means that we have to not assume that the reaction is going to be spontaneous. It may not be. We cannot make any kind of assumptions about cathode and anode. We have to pay attention. So before we start doing these calculations, let's just get a refresher on the equations that we need to use for calculating delta G. We're going to be using negative NFE cell. N is going to be the number of electrons that we exchange. F is our constant, Faraday's constant, 96,500 joules per volts per mole. The E cell is cathode minus anode, and red cat, cathode is the reduction, and oil rig, reduction is gain, oxidation is loss. And then also, so many equations, E cell is, I don't think I'm going to quite have enough room. E cell is 0.0592 volts per mole of electron times the log of K. You know, and I'm realizing as I'm writing that, that's not the same one that I used in my first example. I don't want to stress anybody out, so let's switch to the other one. 0.0257 volts over N times the natural log of K. So here we go. We're going to start with our delta G calculation, and we should just head right over to our table of half reactions and not only find the number of electrons that are being exchanged in these half reactions, but also find the voltages that we need. So I'm going to make a note and just I know that this is not complete, but I'm going to make a note of the rough outline of our half reaction. So when I'm coming up with half reactions, I'm just trying to stay consistent with what sort of makes sense. Iron turning into iron makes sense to me. And N2 plus H2O, 4H2O, turning into N2H4 and 4OH minus. That one also makes sense to me as well. So now I'm going to head over to my reduction potential, and the first thing I'm going to look for is the iron 2, iron 3 half reaction. And let's see, I think actually it would probably be easier if we do this with the alphabetical version. So let's open up that one. Iron 2 and iron 3, I've got it right here. In this reaction, I'm looking for 2 things. I'm looking for where are and how many are there of the electrons. So the electrons, there's 1 per 1 Fe3 plus on the same side. So that's the first thing that I'm going to take care of. I'm going to go to the same side as the Fe3 plus. Same side as the Fe3 plus, that's right here. And I want 1 electron per 1 Fe3 plus. Since I have 4 Fe3 pluses, I need 4 electrons for that. And now let's grab that voltage. That voltage is 0.771. And so now we're going to do the same thing for this next reaction. The easiest thing to look for is going to be the nitrogen and N2H4. And I know that the electrons are going to be on the left side of this reaction because they were on the right side of the other reaction. So alphabetical, we have our nitrogen and our N2H4. For every 1 nitrogen on the same side of the equation, I'm going to need 4 electrons. For every 1 nitrogen, I need 4 electrons, and the voltage on that half reaction is negative 1.16. So with this, we can calculate our E cell, cathode minus anode, which is which? Oxidation is loss of electrons. That's where electrons are being produced. So this is our oxidation. So that means this other reaction is our reduction. Reduction is gain. Reduction is taking place at the cathode. Oxidation is taking place at the anode. So our E cell is negative 1.16 volts minus 0.771 volts. Looks like it's a really good thing that we did not assume that this reaction was going to be spontaneous, because it is not. Our voltage is negative 1.931 volts. The other thing that we need to figure out in order to use our delta G equation, the other thing we need to figure out is N. How many electrons are being exchanged in this reaction? So we've got 4 electrons and 4 electrons in each of our half reactions. So that is the value of N. We're totally ready to use delta G. Delta G is negative 4, the number of electrons being exchanged, times 96,500 joules per volt mole, times our E cell, which is negative 1.931 volts. Don't forget to pay attention to the negative signs here. We're going to get a positive delta G. It's a pretty big number, so I'm going to immediately convert it into joules by dividing by 1,000. And I am going to get positive 745 kilojoules per mole. Again, I just did that joule to kilojoule conversion immediately because it was a very big number. So there's the first part. There's our delta G, and now we need to calculate K. To calculate K, we're going to use E cell equals 0.0257 volts over N times the natural log of K. And we know that our E cell is negative 1.931 volts. And we also know that N is 4. And so we're going to do some math here. Negative 1.931 times 4, divide that by 0.0257, and we get negative 301 is equal to the natural log of K. Undo that natural log. Whoa. K is 3 times 10 to the negative 131. That's a really small number, really, really crazy small. And again, your calculator may not be able to calculate a number that's that small. If you're panicking right now about, oh my gosh, what are you going to do with Alex? The problems on Alex are not this extreme. So you won't have any problem with those calculations. But, ooh, that's a very little number. Let's practice this again. Do we have the same equation on here again? We sure do. How handy is that? That was awfully nice of me. So for this next reaction, we're going to calculate delta G using negative NFE cell. And we're going to look at our half reaction. So one of our half reactions is right here. We've got 2Br2 going to 4Br minus, and we're going to need to fill some electrons in there. And then our other half reaction, N2H2 plus 4OH minus, going to N2 plus 2H2O. And this is the same reaction that we used up here. There. It is turned around. It's going in the other direction, but that's okay because we know what the E cell is. We can fill that in. Let's start by filling in the electrons for this half reaction. So we already looked up 4 electrons for every 1 N2. We have 4 electrons for every 1 and 2. And the E for this is negative 1.16 volts. So we only have to go looking for bromine on our table. Let's go find bromine. And we've got our bromine is right here. And we can see that there are 2 electrons for every 1 Br2. So let's fill that in. 2 electrons for every 1 Br2. We have 2 of the Br2s, which means we need a total of 4 electrons. And let's look back over and grab the voltage on that. I can see from the arrow I made, it's 1.066. In order for us to be able to plug this into E-cell correctly, we need to know what's what. Looking at the position of the electrons, oxidation is loss. So this is our oxidation. Reduction is gain. So this is our reduction. Red cat, this is the cathode. And the other one is at the anode. Oxidation is at the anode. So our E-cell, which is cathode minus anode, is going to be 1.066 minus negative 1.16. 1.066 minus negative 1.16 gives us a voltage of 2.226. So we are now able to calculate delta G. N, we can see from the equation, is 4. F is 96500 joules per volt mole. E is 2.226 volts. 4 times 96500 times 2.226. Again, really big, so I'm going to be dividing by 1,000 immediately to put it into kilojoules. 859 kilojoules per mole. Negative 859 kilojoules per mole. So there's our delta G. And now we are ready to calculate K. To calculate K, we're going to use E-cell equals 0.0257 volts over N times the natural log of K. E-cell is, where is it? There it is, 2.226 volts times 0.0257 over our N is 4 times the natural log of K. We'll let our calculator do the magic. 2.226 times 4 divided by 0.0257. Oh man, these just keep getting crazier and crazier. 3 times 10 to the 150. I'm such a nerd about being so excited about these massive K values. Okay, so you've got one more. We have one more to practice. And what I want you to do, see if you can do it. Pause the video and see if you can do this problem. I'm going to solve it really, really fast. So when you think you have an answer, come back and see what I'm doing. So I did that pretty fast, but I think I got it right. If I made a mistake on there, let me know.